that's why I wanted. That's why I specifically asked. So what's the result?
The result is going to be 130 because all it is.
Are you gonna upload the lecture in lab right after? Lab?
Yes.
Yep. Subtract a bit pattern for a bit pattern, you get a carry, but then you get a smaller number.
Yep. Definitely want to do it here because the internet access here is much faster.
Did you say you were gonna put the answers to some of the practice questions you wrote?
Well, I'm going. Yes. So if on Saturday you still do not get the solution, because I will send an email to the whole class about the solutions. So if you don't get it by Saturday, just kind of send me emails to you guys so that I would get on it and give you the solution, or at least one of the solutions, because there are many ways to do the same thing. All right, so we need to fix this problem. Okay, so it's a trim, and that is not where the problem is. I think this one is where the problem is. Okay.
The wrong answer, right?
Yes and no.
Which is why there's an overflow flag, because it's telling us that that's not.
Yeah, because you're getting 125, subtracting 5, you get a negative 10. Yeah, you're getting 1, that's not good.
So we check the overflow flag, and it's like, yeah, this is wrong.
Yeah, basically, yeah, because just looking at the parameters and the result, you got to want the S number. That's what the overflow flag is telling
Okay, so I'm getting back to the compare.ram file. The assembler itself, is having the problem. So I just fixed that. And we load the program back into LogicSim. And now we can execute the program. Okay, so. So the class is there now?
Yeah, there's a whole, no, in that, in the class right across from this.
Oh, okay.
Like 127.
Oh, the wrong classroom. Yeah. 127, interestingly, is not a CIS classroom, even though it's amongst it's the Art New Media classroom.
Oh wow.
That's why you don't. That's why you don't.
Super warm in there.
Is it?
Yeah.
They crank up the heat.
Oh, either that. It felt like maybe all the computers are like.
They even have Macs over there too. It's a Mac lab. Yep.
Well, since also I can't do this.
Sorry?
Do Macs run hot? Do Macs run hot?
I do not think so. I mean, they use the same processors as PCs, so they use Intel processors. And
I don't know. The system architecture would.
Who needs clock scaling when you have a fan?
Sorry?
Who needs clock scaling when you have a fan?
A fan, but that's air cooling. It's not efficient. You need coolant.
What I do is in the winter just have a bunch of Bitcoin miners running. You don't have to ever run your heater. Yeah, you don't have to ever run your heater.
Okay, so I got the second instruction already done. So we have the 251 in register A. We have the 125 in register B at this point. So now we're going to do a B minus A with the instruction 9-4. So let's go ahead and take a look at the ALU. Okay, so there we go. We have the ALU. Single step, single step, single step. Are we done here? Let's see. Okay, so now the ALU is actually working. The way I can tell it's working is because this is the only instruction that should trigger ALU enable to be a 1. So when the ALU enable is a 1, I know the ALU is being in use and we are currently executing the subtract instruction. So when we execute the subtract instruction, there are a few things you can do. So this is the kind of stuff that you can do when you're studying. You can look into this line here, and it tells you the bit pattern of in 1 into the ALU is 0, 111, 1101, which is also known as 125, that's in decimal, which is the first operand. Okay, so we got that right. The second one is supposed to be 251. So we click on that wire, and it has 1111, 1011. And this is the sign interpretation. In other words, your logistic always use the sign interpretation to give you the decimal representation of that. But that's exactly what -5 is. Yep.
So in hexadecimal, it's 70 and FB.
In this will be F B.
Right, and then the one above is 70.
Sorry?
The one above it was 70.
7B.
Yeah. The in one.
Yeah, in one is a 7D.
7D.
Yeah, that's a 7D because it's a 1101, so it's a 7D. Yep. So the output is what we're interested in. So the output is, well, let's try to work this out first. Because I want to do it by hand first, and then we double check and see whether the output of the ALU is correct or not. So we'll go ahead and do the arithmetic by hand. So we have a 7B minus a FB in hexadecimal. And we can definitely do arithmetic in hexadecimal, because in this case, D minus B is an easy one, because D is more than B. They're off by how many? 2. Off by 2. Very good. Okay, so that's an easy one. So we have a 2 here. And this one is a little bit harder because we end up with a borrow. So we know there's a borrow here. So in other words, we are really subtracting F, which is 15, from 17 in hexadecimal, which is a 23, because it's 16 plus 7, right? Yeah, 16 plus 7 is 23. So 23 minus 15 is 8. Okay, so we have an 8 over here. So we have an 8-2. And since it's an 8-2, we know already that the sign flag is going to be a 1, because anything that is at least 8 for the most significant nibble of a byte is going to have the sign flag set. Okay, so now we switch back into the ALU and click the output of the ALU, which is this wire. It has 8-2, okay, because 1000 is an 8. 0010 is a 2, so we have 8-2. So the way we did the calculation by hand is correct, which is good. That's good confirmation. And it is interpreted as a sign value of -126. So the other things that we also want to check are the flags. Okay, how are the flags being set? You can click on flags out. Okay, it would actually give you the result of flags. So in this case, but you have to remember the positioning of the flags, and it is CZ. SOL. Okay, the carry flag is a 1, makes sense. 0 flag is a 0, makes sense. Sign flag is a 1, makes sense. Overflow flag is a 1. We explained that earlier. That makes sense. And then because these two are the same, the L flag is a 0. Yep.
So the sign flag gets tripped or gets turned to a 1 when your result is a signed number.
Whenever the result has the 8-bit bit 7 being a 1, the sign flag is going to be set, because it really is just a tap out of that flag, out of that bit. So in order to understand that part, that's a good question, but when you look into how the flags are mapped, this will show you, because all we do is look at the output of the mux. This is the actual output of the entire ALU, and we just tap bit 7 to become the sign flag. So the sign flag is no more than just bit 7 of the result, which also means the shift operation, the bitwise NOT operation, bitwise AND, and bitwise OR operation, they all affect the sign flag.
So every operation?
Every operation will affect the sign flag. Yep. Question?
I guess just a refresher on the overflow, because what it's looking like to me is the overflow means we're gonna get a bad answer.
It's not exactly a bad answer. So the definition of the overflow is done here. So this is also what you need to study. Okay, this is a part of what I expect people to actually study, and also bring this to the exam. Okay, you print this out, bring it to the exam, because you might need it to answer some questions. So when you look at this thing here, we see that the overflow flag is done this way. Okay, so depending on what operation, this part is used for addition and this part is used for subtraction. Because when you look at this mux here, it uses exactly the same control line or the same selection line as the ALUOP line. Okay, so the way you choose what operations you're performing is also fed into here. So the input into this mux is basically just a various way of coming up with overflow, depending on whether you're adding, which is this input 0, or whether you're subtracting, which is input 1. For all the other operations, for bitwise AND, bitwise NOT, bitwise OR, the shift operation, I'm just using whatever the input is. So I'm not changing the overflow flag for all of those other operations because it doesn't make sense. What is the overflow condition for right shifting? Who knows? It doesn't make any sense, right? Is that okay so far? So this is important because now we can see the way we determine overflow from a subtraction instruction is to look at the sign flag of the first number, look at the sign flag of the second number. And the way it is used is this is one way to do it, which is a not S1 and and S2. And then we also have to end the output of the operation, which is the difference. So S out is the sign of the difference after a subtraction. Is that okay?
The sign's going in and the sign's going in.
So this is basically we talked about this already, as an equation. So when you use this representation, A blah 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 minus B blah blah blah, A being a bit, and you end up with a C blah blah blah. If you look at only this portion, which is the most significant bits of the numbers as the input, these two are inputs and this is the output, then the overflow flag is going to be when A is positive, when A is negative, and B is positive. Okay, so what happens when you subtract a non-negative number from a negative number? What is the expected sign of the result? It will be a negative number. Okay, you're subtracting a non-negative quantity from a negative quantity. The result is supposed to be negative. What if it is
Positive.
What if it's positive? Then you have an overflow. So this is one way to have the overflow, because A is negative, A is negative, B is non-negative, C is also non-negative. Okay, and then the other way to have an overflow situation is when A itself is non-negative, and you're subtracting a negative quantity from it, but somehow you end up with a negative value. Okay, and this is captured in this part of the logic gate. So it's really representing the same thing. This is the OR. These are the individual ANDs, and then by using the bubbles, I can say what to negate and what not to negate. So this part here is important. The design of the ALU is what actually determines the values of the flags at the gate level. Is that okay? All right. So if that is okay, then we're done with this particular example. We don't want to close it. We want to go switch back to the spreadsheet. All right. Oh, I don't. No, I don't need a new sheet. Click the wrong button. And it just gave me a new sheet, which is okay. All right. So are there any questions about this one? This is actually a fairly good way to study, is just to write simple code, predict what the program is supposed to do, and then check the actual output from the simulator. Yep.
Can you do the other overflow condition?
The other overflow condition, okay. So the other overflow condition is going to be, so we just handled the one where we subtract a negative quantity from a non-negative quantity. In other words, we just handled this one, so we'll do the other one, okay. So the other one is, let's see, I think we can do just the opposite of this. So A is -5, and we can subtract -125 from it.
So which one of those two conditions did we just satisfy?
Okay, so in this case, B is non-negative, and A is negative. So So we have, well, unfortunately, I use the same letters here, and that's why we have a little bit of confusion here. So B is actually this number here, and B is a 0, which means we just handled this case. Okay, so we want to change it to the other one. We now want to handle this case, where the first number is a negative quantity, the second value is a non-negative quantity, and it will still overflow. Okay, and the way to do this in a very lazy way is to reverse these two. That would do it, right? Because now what we will end up with doing is we are subtracting 125 from -5. Well, what is the value? What is the actual value of that subtraction? If you subtract 125 from -5, you end up with -130, right? But -130 is less than the least number or the least value you can represent using a signed 8-bit number, which is -128. So the overflow will be triggered again. Is that okay? All right, so we'll give it a try and see what happens. So go to the assembler, and the assembler, the assembler is now kind of a little sensitive. I don't know why, but I'm just hand checking, making sure this part is okay, and it is. And then we look at the RAM file. Okay, this looks okay to me. So we just go ahead and save, download as, comma separate the value, and we'll do, well, we can use the same file name, compare.ram, COM. There we go, replace it, go back to the simulator, and remember to reset the whole thing. Oh, go back to main, reset the whole thing, reload the RAM file from compare.ram, and single step through it. Okay. So the first two instructions have not changed. It's the third instruction that has changed. So we wait until the ALU enable flag is a 1. Now we can check. Input 1 is now -5. Input 2 is now 125. So that means we are subtracting 125 from -5. We check the output. It is 126. What the?
That's right.
That's right. It is exactly right. So it doesn't make sense, right? Because we're expecting to see -130, and yet we are seeing 126. So the sign doesn't make sense. And as a result, the overflow flag should be set in this case. Is that making any sense? But what about the other flags? Let's check out the other flags in this case, okay? Are you okay, Luke?
Every time my brain tries to make sense of something, like even when you were saying, this is what we're doing right here, you were standing right in front of it. It's just driving me nuts. And then I'll try and look over here to see, like, okay, so this up, and then this screen changes. It's just, I'm just having frustrating issues over here.
Okay. So, how can I do differently?
I don't know. It's like I gotta get a starting place. Go from there.
Well, it's all getting
Okay.
recorded, so there is that at least.
It's probably just one of those things you have to watch over and over, and then it's just gonna click. Like now it makes sense.
Well, what was the last
What
thing
does he explain?
that you just did?
It's explaining the way the overflow flag is the way it is.
Right.
Like
So
why it works, or
Yeah.
what is it for?
What it means.
Well, it's for sign numbers.
Like, he's explaining why it works.
Yeah, he's explaining how it
So
works.
can you start with
You had trouble.
start with the problem that you started
subtracting.
with, where
Go look at the board.
you started with, okay, this
Remember I
is
explained it to you.
what we
It's
want
not-
to do. We want to subtract this from this, and how you were writing it in the assembly language.
I didn't understand I understand how
it did not.
works.
Well, because we're looking at the situations where it will end up with an overflow. That was the question, right? The question is, how do we get it to overflow? And somebody asked, how do we get it to use the other condition to set the overflow? So we use this one with the problem that we started in the classroom. We double checked, we verified that one, we ran the code, and we double checked the flags, did reflect that the overflow flag is set. So now we want the other condition that can set the overflow, which is this one here. So with this one, we have the first number being a negative value, the second number being a non-negative value, and we want the result, the sign of the result to not make sense, which means it has to be a non-negative value. Because normally when you subtract a negative quantity from a non-negative quantity, no, the other way around, when you subtract a non-negative quantity from a negative quantity, you should end up with a negative quantity.
But if you get a positive quantity, then it's wrong.
When you get a non-negative one, then the sign doesn't make sense.
That's right.
So the example that I'm using right now is illustrating just that.
Can you show me what you originally wrote in the assembly code?
I have that erased already, but the difference is minor. Okay, the difference is when you go to the source.
LDI 255.
No, the only difference is how we arrange the A and the B.
There we go.
I just flipped it. So the original code had B, comma A, and now I have A, comma B.
So here.
So it's subtracting B from A, right? So it's
A
subtracting.
minus B.
It is A minus B, correct? Yep. Go ahead.
No idea where to start.
Sorry, the flags will be changed too. Yes. So the flags will be changed, but I'm using the this one here to illustrate how the flags should be set, and then I'll go back and comment the other one. Okay. So when we look at this one, okay, what is the carry flag?
Like 0.
Okay, like.
Because we did not end up with a borrow.
T equals star A.
Okay, Shane, let's stay with this stuff here.
I'm trying to do the
I know,
example you
but the
posted.
class needs a particular point of focus. So when you're doing that, you're having a branch.
I get it.
Okay.
I figure I'm gonna have a question in the middle of this.
Okay, so when you do have a question, and when I'm done talking about this, we'll go address your question. So we can only have one focus. It's just like with any GUI screen, we can only have one focus. You cannot have two text boxes being active at the same time, right? Okay, so let's have this as our current focus. So I will address your question later. Okay, so I'll get to that. What about the Z flag? The Z flag is the 0 flag. So should the Z flag be a 1 or a 0?
0.
Should be a 0. Okay. Okay. Okay.
Well, if it's flipped, then why are we looking at this one?
Why are we looking at this one?
Well, because last time was above it. What we're doing this time is below it.
Yeah, this is what we did, and this is the flipped one.
Well, what are we looking at in assembly code?
In assembly code,
Yeah.
this is reflecting this.
So 251 minus 125 is FB.
No,
minus
remember
70.
251 is, well, okay, this is a bitwise operation. So 255 is FB in hexadecimal, 125 is 7D in hexadecimal.
Well, then where did the 70 minus FB come from?
What?
He went either A minus B or B minus A. That's
Yeah,
Okay, so you just
yeah. One of them's A minus
swapped
B.
the A and the B right
yes,
there?
I did.
Okay.
That is what I did. So now, right now, I'm trying to figure out what happens to all the flags because of this change.
Okay.
Okay, so the Z flag is the next one. So now we have the sign flag. So the sign flag is the most significant bit of the result. Is that a 1 or not? It is not.
It's a 0.
It's a 0. And what about the overflow flag? Well, this is the other way to set the overflow flags. The overflow flag is going to be a 1. So what about the L flag? L flag is a 1 because it's the exclusive OR between the sign and the overflow flag. Okay, but does it make sense? Okay, in other words, in the signed comparison, we are comparing 251 to 125. In the unsigned comparison, which is what the carry flag is about, is 251 less than 125 unsigned? Not, right? No. 251 is not less than 125, which is the unsigned interpretation, and therefore the carry flag is a 0. Makes sense. What about in a signed interpretation as a compare? In this case, if it is interpreted signed, FB is representing the quantity of -5, and 125 is still 125, so is -5 less than 125 as values? The answer is yes, and the L flag being a 1 makes sense. Okay, so I just want to make sure that we have a sanity check and make sure that everything is making sense, when we work on this by hand. Okay, so now what I'll do is I'm going to copy this and overwrite this part here, just so that the comments are consistent. Okay, and then we can just run the code. Okay, the code is already being run here. So now we have input 1, which is the first number being -5, and then input 2 being the second number is 125. The end result is 126. Okay, because that's the actual bit pattern. But we want to look at the flags too. So when we look at the flags, we look at flags out, okay, this is the actual output.
That's doing a subtraction.
Huh?
That's doing a subtraction, right?
It is a subtraction. We know it's a subtraction because that's what we specified. So in this case, if we are looking at flags as the output, we have a carry flag of 0, that's correct. A 0 flag of a 0, which is correct. A sign flag of 0, that's correct. A overflow flag being a 1, that's correct. And then the L flag is a 1 as well, that is correct as well. In other words, the behavior of the simulator running that code is consistent with our understanding of how the flags should be set. But that's how you can use the simulator to help you study. Because when you run the simulator, you're no longer looking at just a static description of what the processor is designed. You can actually make it work, and you can probe those wires to figure out, okay, what is the value presented on this wire at this point? Yep.
Do you think it would be pertinent to go over the addition overflows also?
The addition overflow?
Yeah.
Well, okay, so one question you can try to ask yourself. Now, there's another way to make this work too, because if you're only concerned about overflow and stuff like that, you can just work with the ALU itself. Okay, so unless you want to kind of practice how to assemble the program and put it into the simulator and how to run the simulator, if that is not the focus, you can just run the ALU by itself. Okay, so we'll go ahead and do that. Okay, so let's go ahead and just open the ALU file. Downloads processor. Oh, okay, it doesn't like that. Okay, let me see if I can. Oh, this is now in the downloads folder. This is the ALU. Okay, so now we are just looking at a single ALU by itself. So let's go ahead and think of a way to generate the overflow flag being a 1 using addition this time. Okay, and this time we're only using the ALU, which also means we have to kind of control all of these control lines. Yep.
I was sort of looking for a consistency between the flags and the other flags in the overflow, specifically the sign. What it looks like is if you have the sign flag as a 1 and the overflow flag as a 1, you've reached the overflow in a specific way. And if you have the sign flag a 0 and the overflow flag a 1, you've done it in the other way. Is that pretty much always true? Because like getting to the overflow, there's 2 different ways to do it.
Yep.
The 2 different ways you do it are going to have the sign flag either a 1 or a 0.
Correct.
And that'll tell you which way you
Yep.
sort of achieved the
Yes.
overflow.
Yep, okay, I see what you mean. Yeah. So with the overflow flag being a 1, then you can use the sign flag to differentiate how you got there. And because of that sign flag, you can also know whether it means less than or not. Yep, so you can interpret it that way as well.
So
Okay.
if we got 256 and we add 1, we should get an overflow?
256, well, you cannot represent 256. We only got 8 bits.
255.
But what is 200? What is 255? Okay, so this is a good question.
That'll have a, it'll be signed negative, and so basically you're gonna have a negative and a positive going in, and you're gonna come out with a positive.
You come up with a 0, but this is addition. But this is addition, so in an addition, how do we set the overflow flag? It's not this anymore. Okay?
It's the other side.
It's the other set, so when you go down here, this circuit here is what is going to determine overflow for addition. This circuit
So, yeah,
here
that-
is used for determining the overflow in a
That'd be
subtraction.
That'd be the top if condition.
This is the one.
Of the.
It basically says if the sign of the numbers that you're processing are the same, but the end result has a different flag, then you have an overflow situation, which makes sense because when you're adding, if you're adding two non-negative numbers, you end up with a negative number. Doesn't make sense. If you're adding two negative numbers and you end up with a non-negative number, it doesn't make sense either. So that's why the way the circuit is done here is different.
Yeah.
So you have to. So one easy way to make this overflow is to have 128 plus 128, or negative 128 plus negative 128. What is the result?
It's going to be positive.
0.
It's going to be 0. Because this one plus this one is a 0 with a carry. Yep. So in this situation, we should end up with the carry being a 1, 0 flag being a 1, the sign flag being a 0, overflow flag being a 1, and in this case the L flag is a 1, but it is useless because the L flag is only useful after a compare or subtraction. It doesn't mean jack after an addition.
Yeah.
Okay, but we can double check. Okay, so let's go ahead and double check everything. We have to enable the ALU so that it actually works. So now we look at the actual output of all the flags. The overflow flag is a 1. Okay, so that's good. So we can check that. The carry flag is a 1, which is what we expected. The sign flag is a 0. Okay, and then the Z flag is a 1 as well. Okay, so we just double checked everything. They are exactly the way we expected. Is that okay? All right. Yep.
In this instance, the Z flag really can't be used very much because we got there sort of specific.
Yeah, the Z flag. There are two ways to set the Z flag, or many ways to set the Z flag after an addition. Because if you add 1 to FF, you end up with a 0.
Right.
So there are many ways to get to a 0 in the case of addition, but in subtraction, you pretty much need. The only way to set the Z flag in a subtraction is the inputs have to be exactly the same.
So that's what I'm thinking though. The Z flag set after an addition doesn't mean much.
Say again?
It doesn't really mean much.
It does not mean much. So addition, the flags after an addition is typically not used
Yeah.
because you don't really use those flags for anything, except for one case. I'll talk about that too. This is a good way to describe that one, in this class, in this lab time. But for the most part, we only care about the flags after a subtraction, but not after an addition, even though the adder also makes changes to all those flags.
Because usually we're doing some sort of compare.
Right, exactly.
Subtraction.
But there's one case where the addition is actually useful. Okay, so I'm going to talk about this one next. So let's switch back to this here, and we'll make a new document. Okay. So this time we want to add two 16-bit numbers instead of 8-bit numbers using our toy processor. How do we do that? We are trying to add two 16-bit numbers instead of 8-bit numbers, but using our toy processor, which only has an 8-bit ALU.
Store the 16-bit number in RAM.
So
We can easily store it in RAM. RAM is that's not the issue. Okay, so how do we represent two numbers?
So are we going to do a jump based on the overflow?
Okay. It has something to do with jumps. Okay, so let's go ahead and look at the representation first. Okay, so we have two numbers. Okay, so let's say we have x and y. So x is a number, but because it's a 16-bit number, it's going to use up 2 bytes, right? Because 1 byte is 8-bit, and y is the same way. Okay. Is that okay? Because x and y are both 16-bit numbers. Yep. Go ahead.
So basically what you're thinking of doing is having first addition of the first 2 bytes, then if there's a carry flag, jump and add 1 to the second.
That's right. Okay, it's called add with carry, but we don't have that instruction, so we have to emulate that instruction using like a bunch of code.
Yeah, that's really neat.
Okay, all right. So how do we represent? We'll pick an easy 16-bit number here. Let's pick
2000.
511. Okay, that's an easy one. So how do we represent 511? Okay, so we want to represent 511. So 511 is broken down to.
You convert it to base 2 first, right?
You can do it in base 2, but without even converting to base 2, we kind of know that. Well, okay, some of you may remember 512 itself is a power of 2, right? Because 512 is 2 to the power of 9. 511 is 2 to the power of 9 minus 1. And that becomes all ones, but now we have 9 ones instead of 8 ones.
I don't even know how to remember something I just heard. Remember from
511 is just 3 segments, all ones, right?
As a binary number, it is 1, 1, 1, 1, 1, 1, 1, 1, 1. As a binary number.
That's 511?
That's 511, correct. You can use a sign.
With the extra one.
With an extra one, because with only 8 ones, we have 255, but then the extra one is representing the quantity of 256. So when you add 256 to 255, you get 511. Okay, so, all right, so X is this number, and we'll make Y a little bit easier. Okay, so let's make Y just 1. Okay, let's see what happens. So 1 is exactly 1, and as a number, as in bits, it's just that. Is that okay? But now we have a big question. The big question is, because now X is represented in 2 bytes, and this processor is byte addressable, now we have to decide, okay, but which byte is corresponding to these bits, and which byte is corresponding to this one single bit. Now we are going to use the convention of least significant byte first, or the little endian convention, which means the bytes that has a lower memory location is representing the least significant bits. The byte that has a higher memory location is going to represent the most significant bits. Is that okay? So that means, if you want to look at this as a complete picture, this is the 16-bit number that we are representing. The most significant portion is represented at the higher address. The least significant portion, the least significant portion is represented as the byte that has a lower location, which is this one. Yep.
So the value in 2 consecutive locations would be FF1.
Yep.
Or
And because my stupid assembler cannot deal with hexadecimal numbers, this is the way to specify the same bit pattern.
yeah, and so the next one would be 1, 0.
Yep, that is correct.
0, 1, 0.
Yep. Okay, so now we know how the numbers are represented. The next question is, what is the code to do the addition? Yep, go ahead.
Shouldn't Y be 1, 0?
It should be 0. Oh, you're right. Okay, 1, 0, because 0 is, this is the least significant byte, this is the most significant byte. Correct. Okay, good job.
Good call.
Yep. Okay, so now we want to do the actual code to do the addition.
I don't get why is that?
Hmm?
Why is which one 256 and the other one
Because the
255?
smaller one is represented first. Least significant is represented first.
The byte that has a lower location is the one representing the least significant bits. Okay. So if you want to represent 0 as 16 bits, okay, it looks like that, right? The most significant bits are these. The least significant bits are these. The least significant bytes are stored at the lower location. That will correspond to the first byte. The most significant bits is stored at the next location, the higher location, which is going to be this byte.
So when you say lower and higher, like in
Address.
in RAM, so you're looking
Yes.
at like it's I don't know. So if it's like here, then its next one's here. That's the higher location. Is that
Yes.
what you're meaning? Like,
Yeah.
like literally like above it in memory.
Well,
address value.
let's just assemble the program as it is. Okay, let's figure out how it is going to be arranged in the output of the assembler, because that would be clear.
So like when you're loading things, it'll be LDI, and then you're gonna get the least significant bits first. And then LDI for the next chunk, you'll get the most significant bits.
Okay.
I get that.
Does that make any sense?
So that's exactly how it is supposed to be arranged in RAM, okay? Location 0 has FF, location 1 has 1. So 1 FF together is representing to 511. Location 2 has 1, location 3 has 0. So 0, 0, 0, 0, 0, 0, 0, 0, and then 0, 0, 0, 0, 0, 0, 1 is representing the quantity of 1.
I don't get why are those particular locations the ones that are chosen?
Because I got nothing else using RAM locations. This is the entire program.
It's just a decision of
I know,
how to do the ordering.
We always start at location 0.
What if program that's like in there and just assume that it's not?
Then we keep adding stuff before that, and then the program will look different. I mean, it will shift all the locations lower. This is the assembler. The assembler is just assuming that we always start at location 0.
Okay.
And since there's nothing else in the program, so byte 255 is going to take up location 0.
All we're doing is assigning variables locations.
Yep.
Okay.
We'll put some more stuff.
Oh yeah, we'll do more stuff, but I'm just assembling the program as we go through this process, just so that we can see how the 16-bit numbers are represented in memory. Are we okay with that?
I'm trying.
Okay, so the code that we need to do is something like this. Okay, so we will have to we have to look at location y plus 1. Oh, this is going to be fun because I can't really do that in. I cannot say y plus 1 in the LDI instruction.
You have to break it into pieces.
Well, there's a way to do it. We can say, x high. So I don't have to do the actual calculation. There we go. Right? So this way, x high is the address of this byte, and y high is the address of that byte.
So now you're just loading. So now that is in essence is loading that value somewhere in memory so that you can recall it whenever you.
Well, I just give it a label so it's so I can deal with it easier in my
what
code.
it's doing though? It's
Huh?
basically putting that value 0 somewhere in memory so that you can get it to it whenever you want.
I can get
Is
to
that what that's doing?
I can get to this byte using the label y high. I can get to this byte using the label x high. So I don't have to do x plus 1. Yep.
Will the final contain anything like this?
That's a good question.
Is the final written?
No.
He's making it right now. Let me say.
Well, I'm collecting ideas. Yes.
For clarification, basically right now all you're doing is doing the same thing, defining variables that we have been doing, but you're giving each variable 2 RAM locations.
Correct. Yes. Yep. And I have a way to refer to the other location easily. That's basically just
The
it.
label for them.
Right.
The jump label.
Oh, I see.
Yep.
They're getting
Okay.
numbers.
Yeah, so you have to split it into 2 and then do the addition, carry over the carry.
Yep.
That's a lot of work.
It is a little bit of work, but I wouldn't say too bad. Yep. Go ahead.
If you were trying to add more than just 1, wouldn't you have to do it wouldn't you have to jump sequentially? So if you're trying to add 15, you'd have to do this 15 times, right?
If you have a 15-byte integer, yes. But this is just a 2-byte integer, so it's already a 16-bit integer. If you have a 32-bit integer, you have to do it 3 times. If you have a 64-bit integer, you have to do it 8 times.
For every byte.
I'm just thinking if you had 256,
Uh-huh.
or if you had 511 and you were adding more than just 1, you couldn't just add more than 1 to it. You'd have to do it multiple times because you're
Nope,
adding 1
nope.
multiple times.
Okay, let's figure out what the code looks like. Okay, so let's go ahead and use pseudocode first. Okay, so we'll do pseudocode. So the pseudocode is if x high plus y high ends up with a carry. Okay, so we'll do this first. Okay, yeah, go ahead.
Shouldn't it be x low plus
Yeah,
high low? Or y?
yeah, we probably want to look at
Yep,
those
lows first. Thank you. Okay, so these are all lows.
That's not just use X and Y.
Hmm?
Just use X and Y.
Oh yeah, because the labels just say X and Y right now.
Right. Okay.
Low to just X and Y.
Or we can just do the low here too.
Or yeah, we could
Okay, so
specify.
Okay, so, all right, fine. Here we go. Okay, so we first perform this operation, an 8-bit operation, just adding the least significant bytes. If that operation ends up with a carry, then we want to do the following. So we want to do the x high plus equal to y high, and then do an extra +1 here, because that +1 is because of this carry. And then the else is just doing the same thing, but without that extra 1. So this is basically what we want to do.
So we could actually take that else, put it before the if, and then only execute the if with just adding 1 to x high.
Yes. We can first perform that operation, and then you don't need a complicated addition.
And then that's the whole program right there?
Yep.
Cool.
So the other way to do this, as Cyprian, said, Cyprian, right? Yep. So is to put this here because this part is unconditional. So then you can say just add 1 to it at a constant of 1, and you don't need this part anymore. It represents exactly the same logic. It's just the ordering is a little bit different. So we first perform the most significant byte addition unconditionally, because we have to do that part anyway. And then we perform the least significant byte addition. If the least significant byte addition ends up with a carry, then we just say, oops, we forgot that 1 from earlier, so we just add 1 to it. Is that okay? Okay, so when you look at, the other way to look at this is to use the usual way of adding. Okay, and this is a little on the faint side. Okay, so this is the usual way we perform addition, something plus something. But this time we have 16 bits instead of 8 bits. Okay? When you look at the result here, we break it into 2 halves, okay, two additions. The least significant byte plus the least significant byte with add here. That part is easy peasy. But the problem is, by adding the least significant bytes, we might end up with a 1 as a carry to the least significant byte of the most significant byte. The least significant bit of the most significant byte. Is that okay? So we have to remember to add this extra 1, depending on whether the least significant byte addition ends up with a carry.
That makes sense.
That make sense?
Oh.
Yep.
So you basically took like in that case, like you took the 0.000000001 plus 0.00000, and then you got a result.
Mm-hmm.
And so now you know that result is let's say result most significant, and then you did 1 plus the 0.00001,
Mm-hmm.
and then you have result less significant,
Mm-hmm.
and then but this results in carry, so you say, oh, since there's a carry, then if there's a carry here, then this one plus 1 to this to bring over the carry.
Yep. Exactly.
And then then together they will result that will represent the answer.
Correct.
So this is how you can do operations without big enough registers through using memory, basically, and the flags.
Well, this is how you can use an 8-bit processor to perform 32-bit add and 64-bit add and so on, because you can just stack on this one. Yep.
So when you're coding, if you're using an 8-bit processor,
Yep.
or
I don't know.
well, so
He said it's faster than
you've got an
regular
integer specified as
He said
long.
that's the only way it works.
Your
Then,
you've
yeah,
got a
then
number
that's how he did
specified
it.
as long.
That has to be how he did it then.
And that's its type. And
Break
if
it
you're adding
into
another
one big binary
integer
number and then a binary addition on it.
variable specified as long type.
Mhm.
That's
So if you did a
8-bit
64-bit number,
Okay, Shane, I'm trying to
Oh,
listen
sorry.
to him. Sorry.
8-bit
Yeah.
architecture can't just do those using its registers. It has
Yes.
to do stuff like this.
Yes. So that's why, with a 32-bit processor, it can do 64-bit integers just fine, because it just breaks it up into multiple instructions.
It takes a lot longer than the right, because you have to use memory.
Some processors, like the Intel processor, has an add with carry instruction, which automatically factors in the carry of the previous add instruction to the current add instruction. So that makes it very easy. But our processor doesn't have the add with carry instruction, so that's why it's a little bit more tricky. Yep.
So with our 64-bit, with today's 64-bit processors, well, like say you're in C++ or something, how would you say I want to add to what 128-bit numbers?
Well, you have to look into the NCC standard and look at the documentation specific to the compiler that you deal with, because what long really means depends on the compiler. Okay, some compilers may look at long and say, oh, it's a 64-bit number, and other ones may look at it and go like, oh, this is a 128-bit number. But what if you have something that is not representable using your compiler? Well, you just make it up. You make up your own type, you make up your own addition, your own subtraction, and your own compare operations. If you're in C++, you can just overload those operators. But then you also have to do the casting too, because if you're given a number that is not like a super long type that you're dealing with, if you're given just an integer, then you need a cast operator to cast the integer into the type that you are defining, the class that you're defining.
I guess that's my question. Does C++ what will the compiler do for you? How far will it go as far as like doing this?
Okay, so I'm not going to answer that question directly, but I will tell you how to find the answer of that one. So you just look up 128-bit integer in C. Okay, and say and look through this. Okay, so you basically have to look up online to find that sort of thing.
Okay.
Okay, so getting back to this one, we are almost there. Okay, so we have to add the most significant bytes first, which is actually not an easy thing to do. Okay, but we can do LDI with X high, LD. Okay, let's pick the other registers. Okay, load up one, and then we load the other one, Y high.
Okay, so LD, what LD does is it's taking.
Why are you overwriting C twice?
Oh, that's right. Okay, thank you. Now we have to do the add.
We're trying to see what the opcode means again. Like, okay, so LD.
Okay, so that's a good question. I'm going to give you the answer that is not an answer. That is kind of the answer to help you find the answer. Okay, so the way you figure out what LD does is to look at its microcode and find out how it orchestrates the control lines of the components of the processor. That is the best way to figure out what it does. Because if I tell you the answer, I am studying for you, which doesn't help you in the final exam. But if you look that up, then you are actually trying to understand how the microcode works, how it orchestrates various components in the processor to get an instruction done. That is studying itself. So I'm giving you an answer that is not a direct answer, but it helps you find the answer yourself. I'm giving you a pointer. You have to do the deep reference part.
That's my new favorite.
Yeah.
And I know it means low dereference.
That's my new favorite thing.
Okay, so we're adding these two. Okay, so that's the first part. And then we perform the second part, which is going to be a boring kind of thing because we just have to do this, right? So now we have to say, oh, did we end up with a borrow with the least significant byte addition? That's an easy one to do. We just say LDI. We can reuse A. Yep, we can surely reuse A. And then we say no C, okay? No carry from the first one. And then we are JC A. And then no C is basically a label that ends up here, which is the end of this particular program. And then over here, we just have to add one to X high, which means we have to do LDIA with X high, do an LD of that into, we can load it back into A if we want to. And then LDIB with 1, add a B, and then we have to store it back. Oh, I forgot all the stores earlier. So we have to do all the stores too. So LDA with X high, and do a ST A with the result, which is in C. And then here we have something like that.
Label, then we'll dereference this so we can store our answer.
Right. In memory. Because otherwise it's only stored in register, which is not where I want it to be.
We want it in memory.
Yes.
At the label location.
Yep. So now we just we perform the add, and then we have to do LDI A with X high again, and do ST A with no can't use that. Use that. There we go. Okay, let me just double check. So these two lines together is basically just saying A equals to X high. And then these two lines together is A plus equal to 1. And then these two lines combined is X high is A.
Why are you calling that label no C?
No carry. Fine.
Well,
Because that means I did not end up with a carry from the least significant byte addition. Oh, you're right. Okay, I messed up here. I totally messed up because it's the wrong polarity.
So you want to do it if there is a carry?
Yep. Okay. Okay, Luke, you got me. Then we have to, you can either do a halt here, or if you prefer one single end at the end, then you have to say, A, end, and then JMP to A, which is the end. Okay, you got me. There we go. Good job. Because we don't have JNC, which would be super handy in this case, but we don't have that. So let me just double check again. A is yes carry. JC to A means yes, there's a carry. Let's add an extra 1. If we do not perform the JC, then we just jump to the end, which is also correct. Okay, very good.
so if there's carry, we jump to yes carry.
Mm-hmm.
If there isn't, we jump to the end.
Yes, correct. Which is very kind of convoluted because as a RISC processor, we don't have a JNC or jump if the carry is cleared.
We could just put the halt instruction right there, right?
Yes, if that is, if the definition is get to a halt instruction, when this program is done, then you can just put a halt instruction in place of these two instructions.
Yeah, so that way, if it doesn't jump, it's automatically going to halt.
Yes.
Then you have to halt at the end here.
Yes, I need a halt at the end, which is
I'm
already
saying,
here.
Like if
at,
you did
at
that.
the end of the X, at the end of the yes carry.
Yeah. So without those, you'll have to
Okay.
put a halt after every time.
Oh, right. But it
Right.
falls through directly because after this instruction, it automatically will fall through to the halt instruction.
It'll go directly to the end after the yes carry if we
Yes.
go yes carry.
Yep.
Okay.
Yep. Go ahead.
So I might be reading it wrong or skip something, but if you've got two numbers and one of them is bigger than bigger than 511. Well, okay, if one is bigger than 511 and the other one's bigger than 1,
Mm-hmm.
how would they add properly?
It will still add. This can handle any 16-bit number add. As long as you don't exceed, as long as the result does not exceed 16 bits, this will get it done.
I'm just wondering where the x high plus y high
Yeah,
is.
we're in trouble if we get a carry on
On the high carry,
on
on
the
the high byte addition.
Right, that's not what I'm worried about, but I'm looking for x high plus y high. Like, how does that work?
You mean this part?
Yeah. Where do we
It's
get that?
basically adding these two numbers. It's adding
0,
this
0,
byte
0, 0, 1.
to this byte here.
Right, but when do we hit that?
When do we?
That's one of the first
When
things
do we
that
get
we
to
do.
that?
We get to do it first. We get to do that first because that's unconditional.
I thought that was conditional.
No, the conditional part is whether we want to add the extra one or not.
Yes.
Because we have to perform the usual add anyway
Yeah.
with the most significant byte. The only question is, did we forget to this extra one from the least significant byte add? And we determined that after we perform the least significant byte add. But this trick is only usable, because this makes the code a lot easier by performing the most significant byte add first. But this tricks only work when we only have 2 bytes. When you have a 4-byte integer and you're trying to use this trick, then you cannot use this trick anymore.
Because you have to carry more than once. Yeah.
Right, exactly. All right, so let's give it a try. Okay, so just make sure the syntax is all correct here. Control A, Control C. Go to my assemble sheet. Specify the source. So the answer, Shane's question a little bit earlier. Now we have X and Y, specified later on. So now the definition of X and Y will now be different. So X is now location 32, and Y is now location 34. So the assembler will do all the counting automatically for you, which is why we have an assembler, so we don't have to do all the counting ourselves. So I'm just double checking all the instructions that involve multiple registers, and some of those are still missing. I don't know why it is doing this. So these guys are all missing.
Strike.
I'm going to do it all the way down just so that I do this for the entire spreadsheet. So now it's all done correctly, except for this X high. Oh, it's not an LD instruction. This is supposed to be LDI instruction. So I specify one instruction incorrectly. Why is that one? LDI, there we go. This is an LDI instruction, not the LD. An LD instruction will only load indirect from a register to another register. So this is an LDI instruction. Okay, so good thing I double checked. So we have all these. And then the add instruction is good. Okay. And then when we look at the output, just make sure everything looks okay. And it does. All right, so let's go ahead and give it a try. Download as, we'll call this one add with carry. ADC for add with carry. .ram. But if you play League of Legends, ADC stands for. None of you play League of Legends?
We're too busy with finals.
Good. Too busy with final is good. Okay. So don't do League.
Busy with league finals.
Okay, so let's do ahead and go load. This is ADC RAM, and we'll run the program. Let it rip. But before we do that, just in case there's a problem, I want to log something. I want to log those 2 locations, X and Y. So we go to RAM, and those are locations 32 to 34. So we basically track 32, 33, 34, and 35 because the byte after 34 is significant as well. So go to file, we specify we want to log everything in adc.log. And then we can go execute the whole thing. We'll go through the simulator itself to go through all the ticks.
I forgot how to use the
Uh-oh. No, that's it. Okay, so we stop the simulator. And then we want to check the locations. 3233 is the actual result. What should it be? How do we represent 512 using 2 hexadecimal bytes?
1 0 and then 0 0.
It's 2 times 256. And 256 is 00 as the least significant byte, and a 1 for the most significant byte. So 512 is going to be a 02 for the most significant byte, and 00 for the least significant byte. Okay, so let's check the RAM location. We go to location, this doesn't look right to me, because location 32 is still with 01 FF instead of a 0200, which is what it is supposed to be. So the program did not work. In fact, we have this location also getting changed. So 6D is not supposed to be there. So somehow we got a 6D into this location.
Wait, isn't that right though? Where does the x variable start?
Let's check the program. So the program starts with x being.
I mean, where does it start location in RAM?
Let's check the assembler then. So in the assembler, the label X is starting at location 33. Oh, okay, so it's off by 1. Okay, so X is location 33, and then Y is location 35. So okay, so I get it offset a little bit, but it still doesn't look right to me. Okay, let's look at this again. So we are looking at 3.3, which is this one.
That's 2.
No, this is 3.3. This is 2.1, which is 3.3. So it's definitely wrong. I mean, it's storing the wrong type of thing in it. Okay, and this one should be a 0.0, and this one should be a 0.2. I have a nagging suspicion that it is because of the assembler, which is the worst kind of problem, because if the assembler is not doing what it's supposed to be doing, we have a problem. Well, when the compiler is within your own tool chain, then you have a bigger problem. So let me just double check this. Okay, so we are putting A into C, we're putting Y into D, we're adding D to C, and then we store everything back into X. Sorry?
That's why it's dangerous to go alone.
Say again?
That's why it's dangerous to go alone.
To go alone.
Yeah. If you're the only one working on your tool chain.
Yes.
Your assembler work.
Okay, but we can look at the log file. So the other tool that we have here is the log file. So we can check out the log file and see what it's logging. So it's temp adc.log, and we only have 2 updates. The first update, and we are logging the wrong locations. So it's storing a FF back into that location. It did not add the 1.
You don't want to tell us.
And then it stored this into the second location.
Why did it store that? Why did it store that?
Well, because I logged the wrong location. This is the least significant byte. This is the most significant byte.
Right.
So it overwrote the most significant byte incorrectly, which is the first few instructions. So that it got that part wrong already. So it has to do with the store here. So we just go back and say, okay, what is in C? C is the result of that. Detective story. So Y high is a 36, X high is a 34. We might have to single step this to.
Try increasing the pump rate.
Well, let's just do this. The correct way to do this is to go through the assembly process by hand and double check the opcode to see if it's right. That's not what I'm going to do, because I am going to do this instead. All right. Okay, so let's go ahead and do it by hand, okay? So we load the most significant byte into the first register and do an indirect. Okay, grab this byte, okay, so everything is good. We specify, this part is wrong. It's loading a 0 into register A again. But in the opcode, it should be loading the address of Y into it. So it was not able to generate a code for the second LDI instruction. So when you look at the output, it is a 2.4. So that okay. So the RAM file has 2.4 as well. But when we look into 7.8 is the indirect, 6C00 is wrong. There should be no 00 here. Okay, well, double check that. Did I?
Wasn't that the first addition?
Wait, hold on a second.
Isn't that the first addition between byte high and X high and?
Ahaha. Okay, I found the problem. This is a super embarrassing operator error, which is forgetting to do this. I think I forgot to do it. That's why. So let's see, adc.ram. I forgot to re-download it. Okay. Save, overwrite. Okay, I'm pretty sure I did not save that. Okay, let's double check. Oh, it is still bad. Okay, we have a problem here because this 2.4 did not come out as a 2.4. It came out as a 0.0.
Is that a problem with Google Sheets again?
So it would seem. Okay, let me save it as a different file and see if it changes the outcome. Okay, so save it as adc1.ram. Okay, so this is a new file. I don't have this file at this point. Okay, so we save it. Switch here and save in adc1.ram.
Why does it do that?
Ask Google.
Yeah, this is a Google thing.
Oh, we'll find just problems all over Google spreadsheets.
So I'm problem solving down to a Google issue.
Just file a bug report saying that you can't use Sheets to implement your assembler. Please fix.
Yeah, your spreadsheet sucks. I cannot implement an assembler using your spreadsheet.
You're bringing down our company.
And I'm gonna sue and ask for compensation for losing all this time.
Did we get a piece of that?
Sorry?
It'd be a literal class action.
Yeah. Do we get a piece of that? We'll get maybe a nickel out of cost.
You guys can claim that you think your tech has lost his reputation as a process, and then I can attach a price tag to my reputation in pesos. Oh, okay. Well, here's Damon.
It's about that time.
It's about that time. Ah. Okay. Okay. So apparently I'm combating with.
You're fighting everything.
I'm fighting everything, but that's not going to stop me.
They might be showing now. They might not have been showing before.
Okay, well, okay, at least I put a 2 here this time, but it's still an FF down here. So it didn't really go, huh?
It does boot.
It does boot, yes.
Computer with
Okay, alright, I'm gonna stop the recorder here. And looks like I have a few more debugging things to do to fix Google's problem.